Hi everyone! So I finally finished my Donut Geometry Notes series and I thought that I will publish it as a single video. So if you want to learn Blender Geometry Notes by recreating the legendary donut itself, you are in the right place. This beginner-friendly tutorial series will cover both the basic and more advanced topics in Geometry Notes. So whether you don't have much experience or just want to explore what Geometry Notes are all about, you are in the right place. Our main goal in this tutorial series will be to recreate the legendary Blender Guru donut entirely using Geometry Notes. So, what are Geometry Notes in Blender? The Blender Geometry Notes system was introduced in Blender 2.92 and had a major rewrite in version 3.0. It is a node-based system similar to the shader editor that allows users to interact with geometry in a non-destructive procedural way. What do I mean by non-destructive? Typically, when modeling, we perform transformations, extrusions, scaling, rotations, move things around using modifiers and many other techniques. But if I made an extrusion 2 hours ago, I can't easily make it a bit longer now. It's late for that. This is known as destructive modeling, and that's perfectly fine. It's a common practice and really nice way to model things. However, in some scenarios, it's nice to have more control and be able to adjust things dynamically. For example, I developed an icicles and snow system. Of course, you can try to model it and sculpt it by hand, but if you then decide to change the building slightly, you need to sculpt that part again, and it's gonna take some time. The Geometry Notes system, as you can see, adapts and works dynamically. By the way, if you would like to try this ice/snow system, you can find a link for it in the description. We can create many unique effects for animation, stylized renders, buildings, terrain generation, and much more. Blender Geometry Notes are becoming more powerful with each release, and learning them can really benefit your workflow. So, without further ado, let's jump into Blender and see how we can use them. This donut is the goal in this series. While the system might not be the fastest or most usable, it showcases the immense power behind Geometry Notes. So, in the first part of this series, we will focus on creating the main dough part and mostly on understanding how this system even works. This is a basic tutorial, so don't worry, you don't need any prior experience with Geometry Notes. Enough talking, let's finally jump into a new blend file and start creating this donut. I'm working with Blender 4.2 in this tutorial series. To start your journey with Geometry Notes, first, inside Blender, you will need to go to the Geometry Notes tab. Here you can see 3 main sections: our classic 3D viewport, the spreadsheet that I will talk about later, and the most important part, the Geometry Notes editor. To create your first system, you just need to have an object selected, like the default cube, and to click this new button here. Great. There you have it, your first Geometry Notes system. To zoom in, you can scroll the wheel on your mouse or press Ctrl and the middle mouse button and drag the mouse. To move around, hold the middle mouse button and move. If you want to move a node, select it with the left mouse button, hold and move it around. Like in the 3D viewport, we also have the N panel here with additional options and a toolbar under the T key with just 3 tools: Select, Annotations and Cut, which allows you to cut through node connections like this. So, when we focus on the Geometry Notes editor, we can see something similar to the shader editor. We have 2 nodes, Group Input and Group Output. You can think of it this way. The input is the state of our object before the Geometry Notes modifier. Yes, Geometry Notes are modifiers and you can see them under the Modifier tab. And the output node represents the state after the Geometry Notes modifier. So, everything in between, where this green wire is right now, will be our workspace for the Geometry Notes setup. Our goal in this series is to create this yummy donut, and we will do that here. First, let's learn how to edit this geometry. One of the most basic operations is transform. To add a new node, you can just use the shortcut Shift-A or click the Add button at the top. Let's search for transform. Now we have created our first node. Great job. To connect it to our system, you can simply place it over the green wire and the Blender will automatically connect it for you. You can also connect nodes manually by dragging the wire from the output of one node to the input of another. While we are on the topic of outputs, let's discuss some terminology. Most of the nodes look like this. They have inputs on the left side with different shapes and colors, and outputs on the right. The most important input type is geometry, represented by the green circle. Some nodes do not have inputs, but we will discuss them later. Another way to create nodes is by dragging the wire from an output and then searching for the node you want to add, such as the transform node. Now, let's talk about the middle part of our node. This is where we have additional settings to tweak. There are hundreds of nodes, each with unique settings giving you endless possibilities. Our transform node has 4 main sections. First, the drop-down list with 2 options. I will leave it on components because matrices are the topics for a different tutorial. Below, we have 3 important sections: translation, rotation and scale, the 3 most basic operations in any 3D software. If I change the value of the transform, as you can see, we can move our cube around. Furthermore, we can rotate and scale it. Let's add another transform node. To duplicate a node, just select it and click Shift-D. Now we can transform even more. You can start to see the power of geometry nodes. Even if we perform many transforms, we can still go back to the initial scaling and change it. Or we can add additional scaling just before everything else. And this is still a modifier, so we can turn it off and still modify our original shape even in edit mode. I hope you can start seeing why this approach can be so powerful. Let's start making our donut then. Let's delete all transforms nodes by selecting them and pressing Ctrl X. This way, the connection between input and output remains. If you use delete, we would need to reconnect them. For now, we have our input geometry, the default cube, in our geometry node system. But this won't be of much use because the donut isn't really a cube. We need to create a more torus-like shape, and we will do it entirely with geometry nodes. First, let's create a circle. To do that, search for curve circle, important, choose curve, not mesh. You will see why in a moment. To preview that node, use the Alt-Shift shortcut. Remember to enable the Node Wrangle add-on for this. As you can see, we have a nice 2-meter diameter circle, a little too big for a donut. Let's adjust the radius and set it to maybe 5 centimeters. As you can see, we can write the numbers directly into nodes even with units. Blender will automatically handle the conversion to meters. As I mentioned before, we need a torus. Currently, we have a circle curve. Curves in Blender have one nice ability, that we can plug a profile into them to create a tube or pipe-like geometry. So, if we plug a smaller circle as a profile, we will be able to create a torus-like shape. Let's do this. To achieve desired results, the best way is to use Curve to Mesh node. Let's search for it by dragging from the output of the circle node, and as you can see, this node has 2 geometric inputs. One of them is for profile curves. Let's duplicate our circle by selecting it and pressing Shift-D. Change the radius to 2.6 cm and finally plug this node in as our curve profile. As you can see, we have created our torus. Great. One useful thing would be to control the radius of the torus outside of the geometry node section. To do something like this, we can drag more outputs from the output node, like that, and plug them into the parameters we want to control in the modifier tab. Here, I want to plug it into both radius values. Let's create one more parameter, and as you can see, under the modifier tab, we now have 2 values. To rename these labels, go under the N panel in the Geometry Nodes section, now Group section, and double-click on the labels to rename them. If you want to know more about the modifier section and how to create interfaces for Geometry Node system, you can check out my other tutorial here. After renaming, we can now control the radius of our donut with these sliders. Great. The next thing I would like to control is the resolution of our donut. I will be using a lot of displacement later, so it would be really nice to have more geometry to work on. We can of course adjust the resolution on the circles, but I prefer a more automated approach. For example, we can use the resample curve node. Let's add it between the curve circle and curve to mesh nodes. And this node changes the number of points in our curves. As you can see, we have 3 different modes. Currently, we have a fixed number of points, but we can use the length option. Now, if we set the length value to something small, we get much more geometry. Let's duplicate this and paste it into the second circle. Now, if I change the dimension of the donut, the resolution adjusts automatically. As you can see, changing the resolution affects the shape of our donut. So, this is still an important parameter worth exposing outside the geometry nodes. But for our displacement, the resample will work great. The last thing that I would like to do in this part is to create a flattened area in the middle of the dough. To do this, I will use another new node, the Scale Elements node. Let's add it. This node allows us to scale geometries around each individual part origin. It is set to face, which is correct for us. Uniform scaling scales the objects in all 3 axes, and we can also specify one scale axis if we wish. If I change the scale, we will have a smaller or bigger donut. You might ask, couldn't we just do the same thing with transform? But this node gives us one powerful feature, the selection socket, the pink one. As you can see, it is diamond shaped. We'll cover the difference between diamond and circle outputs in the next part. Currently, we can think of this as selection. We want only the center part of the donut, this ring, to be scaled. So, how do we select it? With attributes. What are attributes? They are basically pieces of information like a color, a number, a vector, and other types. These values are stored inside the geometry in vertices, in faces, in edges, and so on. The places where the attributes are stored are called domains. To create your own attribute, you can use the Store Named Attribute node. Let's add it, and I want to plug it here. Why is that? The place where we store attributes matters a lot. For example, if we had 4 spheres and we stored a random color for each one, and then added one more sphere, this new sphere would not have this attribute at all. We want to store this attribute here because I want to get that gradient. This gradient is called the spline parameter. Let's add this node. We want to use it here because the spline parameter works only on curves, so we need to use it before our transformation to torus, because the torus is a mesh. As you can see, this is the first node outside the input that doesn't have any input sockets. This node only provides information. To preview attributes, we can use the Ctrl-Shift shortcut. Let's plug both the circle and the spline parameter, factor, output, into the viewer node. Now you can see this gradient. Make sure you have viewport overrides enabled. This gradient represents the progress on the curve. 0 at the start and 1 at the end. Black and white values. To store this attribute, you just need to plug it into the Store Named Attribute node. Ensure that you have the float option selected and that you are storing this information inside points. Let's also name our attribute spline factor. Now, how do we use this attribute for our torus? First, we need to get our attribute here. For that, we can use the named attribute node. I use this node so often that I added it to my quick favorites. You can do this like this. Now, let's search for our attribute that we created, the spline factor. Great. Let's preview it with our viewer node and the Ctrl-Shift shortcut. Excellent. The black values means 0 and the white means 1. The spline factor is a gradient from 0 to 1, so we don't have any doubts about it. However, some attributes can have values much higher, like 1000. No matter if the value is 1 or 1000, Blender will display it as white. So, to see the values, you can enable attribute text under viewport overlays. Now, I want to select this area which has a value of 0. To do that, we can use a simple boolean math operation called equal. Let's drag and search for equal. Set it to 0. The epsilon value tells us the accuracy of this node. If we set it to 0.1, for example, values like 0.03, 0.005 or minus 0.04 will be selected. Let's plug this in as our selection. As you can see, our scaling works perfectly now. Great! Let's analyze our setup a little bit. The creation of the torus was pretty straightforward process. The fun starts with attributes. Here we created our attribute, stored it, and it goes here, with our geometry. We pull it out from the geometry and use it here for our calculations. Finally, we are using the output for our scaling as a selection. This part is called a field, which is extremely powerful, and I will talk about it more in the next tutorial. In the next tutorial, I will explain in more details the concept of fields, sockets, colors and shapes, and much more. Today, I'll introduce you to one of the most fundamental concepts behind geometry nodes. Fields. What are fields? According to Blender 4.2 manual, fundamentally a field is a function, a set of instructions that can transform an arbitrary number of inputs into a single output. So, you can think of it as a set of operations that we need to perform. Actually, we already did it in the first part of this series. This part of our geometry node system is a typical field. It's a really short one, but still a field. As I showed you before, the flow of what happens looks like this. First, we go here and take this geometry with us, and then we search for the spline factor attribute on every single point. Then, for every single point, we perform this operation, the equal node. So, for point 1 we perform this operation, and you can see the results are here in the spreadsheet editor. We haven't talked about this area of the geometry nodes tab before, but I think now is a good time to do that. The spreadsheet editor looks like a big table, somewhat like Excel. Its main purpose is to inspect attributes and field values. On the left side of the spreadsheet, you can see all the different domains that you can switch between. We have basic measure type domains like vertex, edge, face, and face corners. What are face corners, you may ask? According to the Blender documentation, face corner domain attributes are associated with the corners of the face of the mesh. An example is a UV map attribute. To better understand the difference between face corners and other domains, let me show you these examples. As you can see, the vertex data specify a little bit more than just a face, even though they all consist of the same 4 vertices. It is similar to trying to select half of the face. We just get this gradient. Let's go to the second example to better show the difference. Here, we have 2 triangles with indices 0 and 1. We also have 6 vertices, 0, 1, 2, 3, 4 and 5, and 6 corner indices. I assigned different colors for different vertex indices and corner indices. As you can see, if we switch between domains, it looks the same. But let's join these 2 vertices together. Now, if you look at the vertex domain, we no longer have 2 different colors at vertex 0. But if we store our colors under face corner attributes, the 2 colors are still visible. This is because the face corner associates information not only with the vertex, but also with the corresponding face. So we now have only 1 vertex, but the face corner index is still the same. As you can see, indices 0 and 3 still represent the same corners. Great. Let's go back to our spreadsheet. The other remaining domains are curves, point cloud, volume grids, and instances. We can switch between them by just selecting the appropriate tab. Here, we can see the number of elements for each domain type. For example, we have over 2000 vertices. Under the Vertex tab, you can see we have 2 attributes: position, which represents the position of each vertex in 3D space, and spline factor, the one we created before. As you can see, we can preview the value of the spline factor for each vertex. So, let's use our viewer node now. If we plug our attribute node into it, we can get 1 additional column in the spreadsheet labeled viewer. Currently, we are viewing the same attribute, so the values in these 2 columns are the same. Let's preview our equal node. Now we can see checkboxes indicating the results of every single comparison. Most of them are false, which is correct, as most of our donut is black in the viewport. To actually see if the spreadsheet is working, let's add an index node and plug it into the viewer node. Now, under the viewport overlays, enable attribute text, and let's choose 1 index, maybe index 0, the first one. Here it is in the spreadsheet. Now, let's preview back the spline factor attribute, and as you can see, the value is 0, as in the viewport. So, the equal value will be true, and it is. The spreadsheet area can be really useful for checking if your calculations are working as expected, and checking the values of attributes or fields, and few more things. Okay, enough theory for now. Let's start creating our first field using the Geometry Nodes editor and spreadsheet. Our main goal in this tutorial will be to create a displacement effect on our donut. For that, we will create a much complex field than this one, but don't worry, the process will be pretty straightforward. First of all, how can we change the position of our mesh to create a displacement effect? Before, we used the transform node for that. However, the transform node has one issue for our use case. It cannot use fields because the input are circular. What do I mean by that? As you can see, we have many different types of inputs. Colors represent different types of values like float, vector, boolean, and so on. But the shape indicates whenever it can use fields. Essentially, there are 3 types of shapes. A circular shape tells us that the input is a single value, like a single number. Circular inputs cannot accept fields because fields produce separate values for each element of the domain, like a vertex. As we saw before, we have different values of our spline factor attribute for each vertex. So our transform node cannot be used for displacement, only for offsetting geometry. The node that will allow us to do what we want is the set position node. Let's add it. As you can see, in this node we have all three different input shapes. We already talked about the circles. Let's talk about diamond shapes. The diamond shape indicates that the socket can accept a field as an input, so we can have different values for each vertex. It can also accept a single value if you want. The diamond with a dot inside the socket means that the socket can accept a field, but currently it is using a single value. Here we are using a single vector 0, 0, 0. Now that we know everything about sockets, let's try to use them. I want to create a large-scale noise displacement to add initial deformation to our donut. Let's plug in our set position node and think about how displacement works. We want to offset our geometry in its normal direction based on some sort of noise texture. If you don't know what the normal direction is, it's basically a direction that is perpendicular to the surface, like this. To get the normal direction, we can create a node named normal. As you can see, this is another node that doesn't have any input. It provides us with the normal direction, a vector for every single point. If you don't know what a vector is, it is a set of three numbers that represents the transformation or direction in 3D space. You can think of it as a little arrow that tells us how to move from point A to point B. Now, let's plug the normal into the offset input, and as you can see, our donut inflates a lot. This is because we are currently offsetting each point in its own normal direction. So the field is actually working. Every point has a different direction offset. To control the strength of this effect, we can add a vector math scale node. Let's add it and change the scale value. Perfect. This node essentially makes the vector shorter or longer. We need to have really small values, so I would add a simple multiply node, a basic math operation, to change numbers with greater precision. We can also add a value node, which is just a float number. Some nodes are hard to find because if you try to add a multiply node, for example, as you can see, we cannot find it. But if you drag and drop, we can. This is because this node isn't actually a multiply, but a math node. So if you want to find it, we need to search for math. Inside this node we can choose between many different math operations, not only multiply. Now that we know how to offset geometry in the normal direction, we just need to randomize the scale value based on some sort of noise. Let's create that noise with a noise texture node. To preview this noise, we can use a viewer node. Let's change the scale, and now we can create a second vector scale node and plug our noise into it. As you can see, now we have displacement. Perfect. Now, let's increase the contrast a little bit by using a color ramp node. You probably know this node from Blender shader editor, so let's add it and tweak the contrast. Perfect. Our displacement looks great. Our field is getting more complex, but it's pretty straightforward. First, we created a noise texture and increased the contrast. Then, we took the normal direction for each point. Now we scale this vector based on our noise texture. Finally, we make them shorter to control the intensity of the displacement. Now, I would like to have more randomization options for our noise texture. In the shader editor, we have something like a mapping node that allows us to move the noise. Here, we can do something similar but with different nodes. First, let's add a position node. This node outputs the position of each vertex, and this is how the noise texture is mapped by default. if we plug the position into the vector input of the noise texture, as you can see, nothing has changed. Now, let's add a vector math add node. As you can see, if we change the values of the second vector, we are moving our texture around. Great. If you look at the similar setup in the shader editor, we can see clear resemblance between the texture coordinate and position node and vector math and mapping node. We basically do the same thing but in geometry nodes. The last thing I would like to do to this offset is to make it more reusable. To do that, I will select these two nodes and group them using the Ctrl-G shortcut. Now, let's rename it to offset coordinate. It would be nice to have a slider to control the offset outside this group. To do that, let's go inside and create a new node, combine XYZ. This node creates a vector from 3 numbers. Let's plug it into the vector math node and the group input. To exit this group, you can press Tab or click this button. Perfect. Groups are a really nice way to organize your node tree. Furthermore, if we duplicate this group, you can see that now every change we make inside this group will affect all copies of this group, which can be really powerful. Let's plug this input value into our group input node. Change the type to integer and rename the label to seed. Now every time we change the seed value, we'll have a different offset. So this will be it for our first displacement. Now I would like to create a second one, but with a much smaller noise. To do this, I will need more geometry. Let's add subdivision surface node. This node needs no introduction. It's basically a subdivision surface modifier, but in the GeoNodes version. I think level 1 should be enough. Now, let's add a second displacement by duplicating this whole displacement setup. Let's plug it in after, and now we can change the noise scale and play with contrast and displacement strength. Perfect. So, we created our displacement. Great. The last thing I would like to show in this tutorial is remeshing. Remeshing is a process often used in sculpting that allows us to change the topology of geometry automatically, recreating the original shape. We will use it here to create a little more organic results. It is really simple to remesh inside geometry nodes, we only need 2 nodes to do that. Let's add the mesh to volume and volume to mesh nodes. This setup will work basically as a voxel remesh modifier. Let's plug everything in and start adjusting the settings. In the first node we can set the voxel amount higher, maybe around 256. This will work basically as the resolution/voxel scale in the remesh process. The density parameter is responsible for the density of our volume. You can think of it as the density of a cloud. If it's too low, our mesh might shrink, but it will be smoother. If it is too high, our mesh will be the right size, but much more blocky. I think 11 is the right number for density in our case. The threshold value determines what is inside and what is outside the mesh. It's similar to density in the final effect. If we had more uneven clouds, it would control what part of the cloud is converted to the mesh. The adaptive value is some sort of dynamic resolution. If we start simply to bring the value up, our amount of geometry will be reduced and our shape will be simplified, but Blender will try its best to preserve all the details. So, this is basically all for remeshing. The last thing I would like to do is to make this a little bit smoother, because it is a bit blocky now. Normally, we would use a smooth modifier for this. Here, we need to recreate this with nodes, but don't worry, it is just 3 more nodes and only one is new. Let's add setPosition node and a position node. Plug the position into the position input. This time, as you can see, we are not using the offset input, but the position one. What we are doing now is assigning the same position that we already have for every point, so effectively nothing changes. To make this geometry smoother, we can add a blur attribute node between. If we increase the number of iterations, as you can see, we have a nice smoothing effect, which is exactly what we wanted. The blur attribute node will make the transition between different values in your attributes smoother. So it's perfect for making geometry smooth. We'll be using this setup quite often, so let's group it and plug the iteration into the input socket. Now let's rename it to smooth. And that will be it for this tutorial. So, we learned quite a few things and new techniques in this part. We created a powerful displacement field and recreated smooth modifier with fields too. Fields are a really powerful tool and one of the most important concepts in geometry nodes. You can try play with them on your own to better understand this concept. For example, you can try using different textures like Voronoi or even mix multiple textures with mix color nodes. Have fun! In this part, we'll focus on 2 main tasks. First, we'll create a basic version of Icing using a few powerful new nodes. After that, we'll create a gradient attribute and use it as a texture for our dough material. So by the end of this part, you'll have the most basic version of the donut completed, even with some really basic materials. Without further ado, let's jump into Blender and continue working on our geometry nodes system. Before we get to the main topic of this tutorial, let's organize our workspace a little bit. If you select a few nodes and press Ctrl J, a frame will appear. This is a great way to keep things organized. You can change the frame color under the N panel. We can also add a label by pressing F2 key with the selected frame or node. Adjust the font size under the N panel as well. Let's make a few frames like this to tidy things up. Our first task will be to separate the top part of our geometry to create a base mesh for our icing. There are a few ways to separate geometry in Blender, but the most straightforward method is to use separate geometry node. As the name suggests, this node separates geometry based on a selection field. We've already used a similar method with scale elements node, so this process will be pretty straightforward. We just need to think about which field we want to create. Let's switch to the side view. Our goal is to separate the top part of the donut mesh. What attribute could we use for that? The most obvious one that comes to my mind is the position, specifically the position on the z-axis. If we can get the position gradient, then we can use the greater than node to separate the desired part for icing. So, now we have a plan. Let's start by adding the separate geometry node and plugging it in. To get the position information, we need to add the position node. As mentioned earlier, we want to focus on the position in the z-axis. To extract that information from the position node, we need to add a separate XYZ node. This one, similar to the combine XYZ node, splits a vector into 3 numbers, x, y, and z-axis. Let's plug it in and preview this attribute with the Ctrl-Shift shortcut. As you can see, we have a dark gradient in the z-axis direction. Great. Now we can use it to separate the geometry with the help of the greater than node. Let's add it. Now we can control the amount of separated mesh. If you switch between the outputs of the split geometry node, we can preview the top or the bottom part. Great. One thing that bothers me about this field is that it's not very scalable or flexible for the different sizes of donuts. If we change the size of the donut, the selected part will start at the same height, but the selected area will be larger relative to the shape of our big donut. To make this system more flexible, we need to adjust our field. A better approach would be to select not the part that is higher than 1 cm, for example, but maybe the top 20 or 30% of the donut. To do this, we first need to know the height of our donut. Then we can calculate the percentage. The calculation of the height is a great excuse to introduce the attribute statistic node. Let's add it and plug the z-axis into the attribute input. As you can see, this node also takes a geometry input but does not have a geometry output. The purpose of this node is solely for field calculations. And the important thing to note is that all outputs of the attribute statistic node produce a single value. Remember that the circular socket shape indicates that this output has only a single value, in this case a float number. This node calculates various statistics of attributes like mean, median, minimum or maximum values, and few more. The one that interests us is the range. By plugging in the geometry and the attribute into our attribute statistic node, this node will give us the range of z positions, which essentially represents the total height of our geometry. Now we can use this information to calculate the percentage. Let's add a math divide node and set it to 2. I am doing this because I want to consider only the top half of the donut. I don't want icing on the bottom. One thing that I didn't mention before about the math node is this clamp checkbox. When you hover over it, an explanation node will appear. This checkbox will clamp our output values from math node to the range of 0 to 1, which can be really useful sometimes. So, for example, if we have value of 2, the math node outputs 1, because 2 is greater than 1. So it's basically splitting all the upper values. To control the amount of separation, we need to add multiply node and plug it in between the greater than node and the divide node. Now we can select a specific percentage. Perfect. One last thing that can improve the intuitiveness of this field is to reverse its value. What I mean is that if the value gets bigger, the amount of icing should also get bigger. Currently, we have the opposite effect. We can fix that pretty easily. First, let's connect this value to the group input to control it in the modifier section. Now, to reverse this value, we will use a very useful node called the map range node. Let's add it here. The map range node is a math operation node that allows you to manipulate the range of attributes. For example, if you want to have a slider that ranges from 0 to 1, but we want larger values in our node system, like from 0 to 1000, this node will take our values and in that case multiply them by 1000. But we can create much more complex ranges. Here, we want to just invert our values. So for 0, the map range should return 1, and for 1, it should return 0. Let's set the toMin to 1 and the toMax to 0. Now, if we play with the value in the modifier tab, you can see that increasing the parameter gives us more icing. Perfect. That's exactly what we wanted. Now we are ready to proceed with the creation of the icing. Currently, we have just a simple bent plane-like geometry. Adding thickness to it would make it look much better. Currently, there is no solidify node in the geometry node system. But we can recreate this useful modifier quite simple with just 4 nodes. The first step is to add an extrude mesh node. This node allows us to perform, as the name suggests, an extrusion operation. There are a few settings under it, so let's explore them. First, we have a drop-down list that allows us to switch between the extrusion on different parts of geometry, like faces, edges and vertices. Second, the mesh input is just the geometry that you want to perform extrusion on. The selection, just like before, allows us to select the part that you want to extrude. For example, just a few faces, not all of them. Offset is used mainly to specify the custom direction of the extrusion. By default, extrusion is performed in the normal direction, but maybe you want to extrude everything in the direction of the z-axis. We can specify it here with a simple vector. The offset scale is the most important setting that specifies the amount of extrusion. Lastly, the individual checkbox determines if you want to extrude every single element separately or together. So let's uncheck the individual option and set the offset scale to something a little bit smaller. If you look at our geometry from the bottom, we can notice that we don't have any geometry here. We need to fill it. For that, I will use our geometry before extrusion. To join 2 or more geometries together, we can use a really useful node named Join Geometry. It will do exactly this. So, let's add it and plug in both the results of the extrusion and the state before extrusion. As you can see, this is the first node that allows us to plug multiple wires into a single socket. This socket, in the shape of rectangle with half circles at the top and bottom, allows plugging many wires into it. So, we recreated the Solidify modifier. Great. There are 2 technical issues now that we don't see at first glance. The first one is face normal orientation. If you don't know why the normal orientation of the face is important, let's talk about it in the simple example. In games, typically only one side of geometry is visible to the camera. This isn't a problem because we only see meshes from the outside, from the correct side. But if we accidentally get inside a rock or inaccessible building, we can see that these surfaces are often transparent. This is because in 3D modeling software we can specify which side of the geometry is correct, which one is the outside of the geometry. This is called normal face orientation. To preview it, check the face orientation option under the viewport overlays. Now you can see the bottom part of the geometry is red. In Blender, the blue color means the positive side, which you can refer to as outside normal, and to fix our problem we need to flip the normals in the bottom of the icing. Thankfully, this can be done easily with a single node named Flipped Faces. Let's plug it here before Join Geometry node. Now everything is blue. Great. First issue solved. One issue that I notice now are those edges that we can see on the edge of our donut. This is because when we separate our geometry we used point mode, and this can create these edges. We should use the face mode, because with face mode we are separating only faces. So there is no way we're gonna be left with those separated edges. The second technical issue we want to solve is overlapping vertices. When we joined the extrude mesh and the original one, we added this part of the geometry twice. Once with the extruded part and once with the original one. To merge these 2 separated mesh islands together, we can use the Merge by Distance node, which does exactly what the name suggests. Let's add it after the Join Geometry node. And that's it. We created our Solidify modifier. The merge by distance node is really useful and allows for few customizations. First, we can specify the distance. This essentially means that any points closer than this distance are going to be merged together. The drop-down allows us to specify if you want to merge separated mesh islands together. In our case, yes, we do. The selection socket doesn't need any special introduction at this point. The next part will be really simple: remeshing. For that, we can just duplicate our node setup from before. Let's select these three nodes, mesh to volume, volume to mesh and smooth group, and duplicate them with the Shift-D shortcut. Perfect. Our setup works great. We just created basic icing for our donut, which we'll use as a solid base for future adjustments. I think this is a good time to talk about performance. If we enable the timing option in the viewport overlays settings in the Geometry Nodes editor, we can see the time each node takes to execute. This is a great way to identify which parts of your node tree takes the longest to execute. As you can see, our total time is getting longer with each new node. If we continue at this rate, soon we will need to wait few seconds for each change. That would make for a very unpleasant workflow. Fortunately, in the recent Blender release, a new node was added to save our day: the bake node. Let's add it and plug it in at the end. Now, let's click bake. Suddenly, we can perform new operations really quickly. Why is that? Because what this node does is save the calculated geometry on disk. So Blender doesn't calculate that part of the node tree anymore when you change something after the bake node. This is really important because if we change something before it, like the radius of the donut, as you can see, nothing has changed. It will calculate new donut shape only if we click bake again. If you would like to know more about this node, you can check out my other tutorial specifically about the bake node. So, we created the base icing and the donut shape. Let's join them together now with another join node. Great. To assign different materials to the geometry, we need to add a set material node. Let's add one for the icing and one for the dough, just before the join node. This way we can assign different materials. Let's create two materials, one for icing and one for dough. Now we can choose them in the set material node. Perfect. Let's go to the shader editor. Let's change icing material color to pink and slightly yellow / beige / brown for the dough. The last thing we can do to our geometry now is add smooth normals with a set shade smooth node. Great. The second thing I wanted to create in this part is the texture for our donut. In the Blender Guru tutorial, he used texture paint mode to add this color gradient to the donut. But since we are creating everything procedurally, we'll create the texture in geometry nodes too. Our goal now will be to create custom attribute that will look like that. Then we'll use that attribute in our material. So let's start. First, let's drag another wire and search for reroute node. This little tiny node allows us to keep order in our geometry nodes network. You can also create it by holding Shift and the right mouse button and dragging over the existing wire. Now, let's create a store name attribute node and name it texture painting. It will be a float attribute with point domain. To create this gradient, we will again use our position. Let's duplicate the position and separate XYZ node from here. To get nodes out of the frame, you can use the shortcut Alt-P. Now, I want to create a perfect gradient that goes from 0 to 1. We can do this with the Map Range node. Now, we just need to know the minimum and maximum values of the position. We did something really similar before when we needed the range. As you can see, the attribute statistic node also provides us with minimum and maximum outputs. Let's add an attribute statistic node here and plug in the geometry input too. Now we can use the minimum and maximum outputs. Great. We can leave the toMin and toMax values as 0 and 1. Now, to create this type of gradient at the center, we can simply use a color ramp node. Let's add it. If you ever work on procedural materials in Blender, you probably know this node. It essentially works like a map range for colors, but with more intuitive interface. Let's plug our gradient into it. As you can see, if we start to play with these handles, we can change the contrast of our gradient. Let's add a third handle with this plus button. You can remove handles with the minus button. Now, let's place the white color in between, change the third color to black, and now we are ready to go. One thing we could improve in this gradient is to make it a little bit smoother. There's one node perfect for that, and we already use it. Can you guess which node I'm referring to? The blur attribute node. If we add this node here, we can make the transition much smoother. Let's increase the iteration number. Perfect. With this attribute, we are ready to go. Let's make a little bit of order here. I'll join everything from this attribute into a single frame. Let's jump back into the shader editor. To use geometry node's attributes inside the shader editor, we can add an attribute node, just like in geometry nodes. Now, let's copy the name of the attribute and paste it here. If we go to the material view now and preview it, we can see our gradient. Perfect. So, let's use a color ramp again, but this time inside the shader editor. Let's change some dough color to appropriate ones and plug this in as our color. Great. Congratulations! We created the first version of the donut entirely with geometry nodes. Good job! In the next part, we will focus on creating more interesting icing. Thank you so much for watching. I hope you learned something new in this tutorial. If you want to support my channel, you can check out the links in the description for my Blender add-ons and asset packs, and the Blender file for the final donut on this tutorial. In the previous part, we created a basic donut with icing. Today, we'll add basic sprinkles on top of the icing. The main theme of this tutorial will be instancing. First of all, what are instances? They're basically copies of the same geometry, duplicated often thousands of times and used for all sorts of effects, like grass, rocks, or other elements. You can actually create your first instance by hand extremely easily. You just need to select an object, for example the default cube, and press Alt-D. As you can see, similar to Shift-D, now we have two cubes. But when we enter the edit mode, if we change something in the first one, the second cube changes exactly the same. all instances share the same mesh data, which is why we can use even millions of them in a single scene without crashes. It is a very efficient way and saves a lot of memory during rendering. Now that we know what instances are, let's use them to create our sprinkles. Let's jump into our blend file and continue to work on the donut. By the way, if you are new here, you can check out my first part of the series, Introduction to Geometry Nodes. Our first task now will be to separate the area where we want to have sprinkles. First of all, we want them only on the icing, not on the dough. So let's drag a new wire and create a reroute node for now. We have our icing, but we don't want sprinkles on the whole thing, especially not at the bottom, because they won't even be visible. The best approach now will be to separate the geometry where we want our sprinkles. To do that, we'll use the Separate Geometry node. Let's add it after the Reroute node. Now, we need to create the selection field to separate the top part of our geometry. We will use the normal direction for that. Why? The normal direction of the geometry is useful in many cases. We already use it for displacement, but one of the most common use cases is selection based on orientation. This means we can select the part of the geometry that faces a specific direction, like the top part, bottom part, or the side part. To make that selection, we will need two more nodes: the dot product node and the greater than node. Let's plug them in like this. The dot product is a math operation on two vectors that tell us how they are positioned relative to each other. The value of the dot product ranges from -1 to 1. If the value is negative, it means that the angle between two vectors is greater than 90 degrees. If the value is exactly 0, it means that the angle is precisely 90 degrees. If the value is greater than 0, it means that the angle between the vectors is smaller than 90 degrees. It also indicates that the vectors are exact opposites if the value is -1, and they are the same if the value is 1. Dot product is a very useful comparison. Let's specify our second vector as 0, 0, 1. This will be a simple vector that just looks up in the positive z axis. So, we want to select normals that are facing upwards with a little bit of margin. To control that, we can adjust the value in the greater than node. A value of 0.5 works well for our selection. Now that we've selected the geometry where we want to place our sprinkles, it's time to choose the location for our instances. For that, we will use points. The most common approach for instancing with geometry nodes is distributing points on faces or inside volumes, and then placing instances on top of them. This approach is really nice because it enables us to control the density, spacing, and patterns of distributing instances very quickly, as we are not working with real geometries, just points. To create points, we need to add the Distribute Points on Faces node, which does exactly what its name suggests. It distributes points across the faces of the geometry. This node has a few important settings. Let's go over all of them. First, we have a drop-down menu with two options. The Random option distributes points randomly on faces. To better see the difference between random and poison disk, let's increase the density to have more points. As you can see, these points are really big, so it would be more convenient to make them smaller for preview. To do that, we can add a Set Point Radius mode. It allows us to change the size of points. Let's set it maybe to 5 mm. Great. Now we can see all the points on our icing. The density is the most important setting here. It controls how many points we have. It's important to remember that this works with scale, So, the same density will create many more points on bigger objects than on smaller ones. Because we are working with real scaled object and the donut is pretty small, we need to have pretty high numbers in the density. The random mode distributes points randomly. The poison disk mode does this too, but with few additional settings. The main one being distance minimum. This allows us to specify the minimum distance between points, which can be really useful to avoid intersecting geometry. We'll stick with the poison disk option because I want to specify the distance minimum to maybe 3 mm. The selection input works just like before. We can specify where we want to distribute points. The density factor option allows us to control the overall amount of points. You can think of it like this. First, we created 1000 points with a specific minimum distance. And now, we want to have fewer points. The density factor allows you to do that. The last option, seed, allows you to switch between different variations. We can plug this seed into our global seed value from the group input node. Now, we can randomize the sprinkles points from the modifier tab. So, now we have points. Let's put some sprinkles on them. The node that allows us to place instances on top of points is named Instance on Points. Let's add it. This node has several options too. First of all, the points input is where we specify the points on which we want to place our instances. The selection input allows you to choose only specific points, just like with any other selection socket. The pick instance option is used when you have many different instances, like various plants or other meshes. If you use, for example, a whole collection of objects as an instance, this checkbox will randomly switch between different objects in the collection instead of placing all of them on every point. The instance index allows us to specify specific instances. For example, choosing only one from the collection. We will not be using the pick instance option in this course because I want to make each sprinkle completely unique. The two remaining inputs are pretty self-explanatory. The rotation input is for rotating instances, and the scale input is for scaling instances. A little bit of extra theory about instances. First, we cannot change the geometry of individual instances. They must all be the same. However, there are a few things that allow us to create a more varied look. First, as I mentioned before, we can use multiple objects in a single instancing system. We can also randomize the rotation and scale of each instance, creating much more interesting results. Now it's time to create some sort of instance. In a future part, I would like to make each sprinkle different, so we will not use a simple cylinder for the sprinkle mesh. Instead, we will use a curve line. Let's add a curve line node. This node allows you to create a simple curve by specifying the position of the start and end points. It also has a second mode that allows specifying the direction and length of the curve. Why are we using a curve? Because later it will allow us for much more customization. Additionally, we can convert it to a cylinder with a simple curve to mesh and circle profile nodes. So it will look like a cylinder in no time. Let's specify the length. I want to have a vertical line, so we need to adjust the start and end points in the z-axis. Why start and end? Because I want to have the center of the curve in the middle. So when we place the curve on top of the icing, they should touch the icing with the midpoint, not the end point. Let's add a value node and set it to 0.012. This will be our length. I am using a value node because I want to have a single node to control both the start and end points of the curve. Let's add two combine XYZ nodes. Now, we want to set the start point at minus half the length, and the endpoint at half the length in the z-axis. To do that, let's divide our length by 2 with a math divide node. Now let's multiply it by -1 with a math multiply node. We have two values that we can plug into a combine XYZ nodes. Perfect. As you can see, now our curve line is exactly in the middle. Perfect. So, let's join our icing and sprinkles together to better preview what we are doing. As you can see, it would be really nice to align our sprinkles with the icing a little bit more, because currently they're aligned in a single direction. Thanks to the distribute points and faces node, we can do this really easily with the rotation output. Let's plug it into the instance and points, rotation, input, and that's it. Our instances are clearly aligned, but not kinda in the way we want. Currently, the sprinkles are standing. We want to align them horizontally, not vertically. To do that, we just need to rotate them by 90 degrees. But how we can do that if the rotation input is already used? We could try to make a more complex field here, but a much easier solution is to use a simple rotate instances node. With this node, we'll be able to rotate our instances, so let's add it. If you play with the rotation values, you will notice that rotating in the x-axis by 90 degrees does exactly what we wanted. This is because we basically rotate our instance to make them horizontal. We could do exact same thing here, before instancing, with a transform node. As you can see, the result is the same. Great. Now it's time to add a little bit of randomization. Let's add another rotate instance node and a new scale instances node. Let's talk about the inputs of these two nodes a little bit more. The selection input is clear, as well as instances. Notice that it clearly says instances, not geometry. It is designed specifically for instances. The rotation and scale inputs are pretty self-explanatory. The pivot point allows us to specify a specific point which will be the center for scaling or rotation, but currently it is ignored because we have the local space checkbox select. This checkbox allows us to scale or rotate each instance separately along its own origin point, which is what we want in most cases. However, there is a possibility to use a more complex field to specify exact points along which we want to scale or rotate. So, to randomize our sprinkles, we will use two random value nodes. One set to vector and one to float. These nodes will give us random values in specific types. As you can see, we can switch between 4 different types: float, vector, integer, and boolean. Let's play with these values to create a nice randomization. We can also plug these seeds into the group input seed. Great. Now we have perfectly random sprinkles. The one thing that bothers me at this point is that we still have just curved lines. It would be nice to transform them into cylinders. As I said before, we cannot edit the geometry of instances, but what we can do is to convert our instances to normal geometry and then edit them. To convert instances, we can use the Realize Instances node. If you hover over the socket, you can see here we have instances, but here we have curves. You can notice that also inside the spreadsheet editor. There is a selection input to specify which instances we want to realize, as well as a checkbox to realize all. This just realize all instances. The depth option is useful when we don't want to realize all instances in cases where we have nested instances. Nested instances occur when we have instances on one object and then use that object with instances as an instance for another system. So, now that we have created standard curves, let's use curve to mesh and curve circle as a profile to create cylinders. Let's change the radius, check fill caps, and that's it. If we turn off our Realize Instances node with the M key, you can notice that our Curve to Mesh node still works. This is because Blender is smart enough to continue to work with original instance geometry. But keep in mind that we still have the same geometry on all instances. We cannot make them different without realization. For example, if you try to use our displacement setup on them, as you can see, nothing happens. This is because instances don't have normal attribute. Even if we try to set the position with only noise, as you can see, we are moving the whole instances without deforming them. If we unmute the Realize Instances node, we can clearly see the deformed mesh. I will leave the Realize Instances node for now. It will be useful in the future, and I will show you why. So, we created our phased basing particle system with instances inside geometry nodes. Great job! Now, let's join it with the dough and add another material. Today we'll be working on improving our icing. Currently we have a very basic, perfectly circular icing. I want to add a nice randomization wave and even create droplets all inside the geometry nodes. Without further ado, let's jump into Blender. So, last time we created these sprinkles. Today we'll go back to our icing to improve its look significantly. To do that, let's create a new reroute node here to separate our icing mesh. Our first goal will be to make the bottom part of the icing more uneven, because now it looks perfectly cut off. For that, I will show you a new workflow with remeshing. First of all, let's create a mesh to volume node. I want to have a pretty high voxel amount, something like 400 should be good enough. I will also set the density to something bigger, maybe 5. Yep, that looks good. As you remember, before we used this node in combination with volume to mesh to do remeshing. Now we'll do something more advanced. One interesting property of volumes is the ability to distribute points inside of them. To do that, we'll use a distribute points in volume node. As the name suggests, this node allows us to distribute points inside the volume, similarly to distribute points on faces node. It has two modes, but different ones. The random mode works the same, distributing points randomly, but the grid mode distributes points in a regular 3D grid. To actually see the difference, we need to set the density higher. Much higher. The points now are really big. Let's scale them down to better see what we are doing. For that, I will add a set point radius node and set it to 2 mm. Let's increase the density a little more. Again, this is because we are working on a real-life scale and the donut is pretty small. I will set the density to 5 billion. Extremely high, but it works. So, why do we convert our icing into a bunch of points? Because in geometry nodes you can actually convert points to volume and then to mesh. So, this is another way to remesh things. But we'll not do it yet. This is because we didn't change anything in the points. If we convert it to mesh now, the results will be the same as before. This is the part to randomize the bottom part to create this nice wave-like pattern on the edge. So, our current goal is to take these points and delete the bottom part with some sort of wave pattern. Before, for separation, we used the separate geometry node, but now we actually don't need this separated part at all. Because of that, the better approach will be to just delete this unwanted point with delete geometry node, which do exactly what the name suggests. It deletes stuff. Let's add it and plug it in. As you can see, all points have been deleted. This is because by default, delete node will delete every point. Here, we can switch between domains to delete only specific parts of geometry. Here, we have only points, but if we take the default cube, for example, we can delete all faces, and by switching to only faces, the edges and vertices still remain. So, let's leave it on points and all. Now, we need to create a selection field. First, do you have an idea how to select only the bottom part of the icing? What node or information could we use for that? We already did something similar with the z-position attribute. Let's add a position node and separate xyz. Great. Similarly to when we created our color attribute for the dough, I want to have a gradient that starts at 0 and ends at 1. If we preview our position in the spreadsheet, you can see our range is different. Let's use the same solution as before. Let's add an attribute statistic node and plug it in. Now, let's add a map range node and plug in the same z position, and inside from min and from max values, first min value and then max value from the attribute statistic node. Perfect. If we preview it now, you can see we have a perfect gradient in the correct range. That's exactly what we wanted. Let's do a quick reminder. The attribute statistic node allows us to calculate different statistics from plugged attributes and geometry. We needed it here because I want to know what is the smallest and highest value of position on the z-axis. If you look from the side, you can see these values should be here and here. Why do we need those numbers? For the map range node. I want to have a gradient from 0 to 1. To make something like this, I need to know the current range. With the attribute statistic node, I calculated this range and then plugged it into the map range node. Now, I have a perfect gradient. Great. Now, let's add a greater than node to actually make the comparison and select specific parts. let's plug it into the map range node and then into selection. If we play with this value, we can separate different parts of the icing. So, the next question is how to make this more uneven and how to invert that selection, because we want to delete the bottom part, not the top part. Technically, we could use the less than node, but I wanted to show you how easily you can invert selections inside fields. To invert a boolean value, black and white values, you could use just a not node. Let's add it. This is a boolean math operation that basically inverts the selection. So, what was selected is now deselected, and what was deselected is now selected. Great. Now we need to make this deletion uneven. For that, we'll use a noise texture node. Let's add a noise texture as well as the offset coordinates group that we created before. Now, let's join them together and plug our group input seed inside our custom group. Let's preview the noise with the viewer node. Now, our goal is to create a middle-scaled noise texture, something like this. We'll use it with our gradient to make a random selection for the delete node. Currently, for selection, we are using a single value threshold number, here. But you can see the socket is diamond shaped, which means that we can use a field here. For example, our noise. Why? Let's think about what will happen before plugging it in. To make the effect more visible and have more control, we need to have a way to increase the contrast in the noise texture. Let's add a map range node for that and play with the toMin value. I will set it as a negative number. Now, in the viewer node, we can see a clear division between black and white values. So, if we plug our noise into our greater than node and think about the black values, the chances are that most of the bottom will not be selected. This is because our gradient starts at 0 and most of the gradient has a greater value than 0. So, if the noise gets darker, less of the icing will be deleted. Let's think about the white part of the noise now. If you compare white to the gradient, chances are that the white part of the noise will be greater than the bottom part of the icing. Remember, the lowest value of the gradient are at the bottom of the icing. So, it will be deleted. To test our thought process, let's plug in our field. Let's now play with the map range node. And great, everything is working as expected. We have nice irregular icing. Our icing is nicely irregular now. It's time to convert it back to a mesh. For that, I will use the points to volume node. Let's drag and search for it. As you can see, we have a few interesting options. First of all, we can choose between amount or size. For our use case, I will leave it at amount, because I don't want to have much more geometry for bigger donuts. As you can see, in size resolution, we can specify voxel size in meters. In amount mode, we are specifying an arbitrary number. I will set my voxel amount the same as at the beginning of this process, 400. Density works the same as in the mesh to volume node. I will leave it as 1. The more important setting is radius. So, how do the points to volume actually work? It basically puts tiny volume spheres on every single point and then joins everything together. So, the radius parameter is the radius of those spheres. As you can see in this example, we can clearly see those spheres now. And if we change the radius, we can see how it works. So I will set a really tiny radius of something like 1 mm. So now it's time for the classic volume to mesh node. I will leave the settings as default. Our results is really noisy now, but we can fix it with our custom group named Smooth. Let's add it, plug it in, and increase the number of iterations. Great. Our icing is looking nice. So, this is the first part of our process of creating more realistic icing. The second step will be to create those droplets that we can see here. They are a really significant part of the final donut look, so we need to recreate them. How can we make them? The process I came up with looks something like this. First, we select the potential area for droplets utilizing our point cloud. Then, we select just a few points to place our droplets on. Then, we place randomly scaled curve lines, and after that, we convert them to mesh using a custom radius to make them look like droplets. After that, we join it with our current icing and remesh everything together. And like everything before, we will do this with nodes. So, let's head back to the GeoNodes editor. Our first task will be to separate the area where we want to place our droplets. I think the easiest way to do this will be to use our points from here. Let's just add separate geometry node, and now for our selection field I will utilize our gradient for the map range node. Let's add a less than node and plug it in. Let's play with the threshold value now. Great, I think that would be enough. Now we need to select just a few of these hundreds of points. To do that, I will actually delete most of the points randomly. Let's add a delete node again and plug it in after. Now we'll create a really simple field with just two nodes, and one of them will be group input. Let's add it and drag and search for the random value node. Let's set it to a Boolean mode. Now, if we plug that into the delete geometry node, we can specify what percentage we want to delete. Since we want to have just few points, I will set this value really high, something like 0.999 is just right. As you can see, this probability value directly controls the number of points because the random value boolean switches only between two values, true and false, which means delete or not delete. So now it's time to place some instances on these points. We already talked about instances in the last part, so nothing new here. Let's add an instance on points node. For our instance geometry, I want to use a curve line. Let's add it. I want to make them really short, so let's specify the endpoint z coordinate to minus 1.5 centimeters. Let's plug it into the points node. Now I would like to randomize the length of these lines. To do that, we can again use a random value node, this time of float type. What parameter do I want to randomize, you may ask? The instance scale in the z-axis. If we scale those instances randomly in the z-axis, it will produce longer and shorter lines, which is exactly what we want. Let's add a combine XYZ node and plug the vector output into the scale of instances. Perfect, that is exactly what we wanted. As before, to edit the geometry of our instances, we should convert them to real geometry. Especially because we want to make them unique. Let's do that with the Realize Instances node. Now we have a bunch of curves. Our goal now will be to create this droplet-like mesh. To do that, we'll need some divisions on these curve lines. Currently, each line has only 2 points, the end point and the start point. That is too little for our needs. To create nice round droplets, we will need a few more vertical divisions. Luckily, there is a node that will allow us to divide curves evenly. It is called a sample curve node. Let's add it. Do you remember that node from the first part? It will allow us to divide our curves, lines, into segments with even length. To do that, we need to set its mode to length. Now we can specify the length of the segment. I will use something really small like 0.000333 meters. Great. If that number is too low or high, we can change it later. Let's convert our curves to mesh with a simple curve to mesh node. I will use a simple curve circle to create a cylinder-like shape. Let's adjust the profile radius, and that's it. We use this exact same technique for our sprinkles, so it doesn't look much like a droplet, does it? To adjust the shape, we'll specify a custom radius attribute for our curve lines. To do that, we need to add a setCurveRadius node just before the curve2mesh node. Let's add it. What this node allows us to do is to specify a different radius for every single point of the curve. So this is perfect for our use case. We'll need a smaller profile at the beginning, then bigger closer to the end, and a profile with a radius 0 at the very end point. How can we do this? It is a rather complex profile. It would be hard to specify it with just some numbers and slider. Luckily, there's a node that allows us for a much easier graphical approach. First of all, we need a gradient that will go from the start to the end of each curve line. We already used a node that provides us with a gradient for curves. Do you remember its name? It was the spline parameter node that we used in the first part. Let's add it. If you preview this node, you can see we have nice gradients on every single line that start from black and end on white. I am using a factor output that has a range of 0 to 1 rather than the real length. If we connect it to our radius, our droplets start to look like cones. Not the desired results, but we can see that the setRadius node is working as expected. For 0, the radius is 0, and for 1, the value is the biggest. To adjust the effect, we actually need one more node, floatCurve. Let's add it between the spline parameter and setCurveRadius. Now, this node allows us to play with a diagram to create unique results. This node takes the input, linear gradient in our case, and maps it into the new one. The diagram that we specify here allows us to control this transformation. As you can see, we can add new handles by just tapping. We can move them, adjust them with sliders, and delete them. This node is often used for setting radius. So, we want to have a small radius at the beginning, then we want to have a bigger radius. And at the end, the radius should be 0. Let's play a little bit with it. And perfect. That's exactly what we wanted. Great job. So, the last part will be to remesh everything together. To do that, let's first join the droplet with the icing with a simple join node. Now we are ready to convert it back to volume. One useful thing with remeshing is that it enables you to join completely separated geometries. Let's add a mesh to volume node. we'll again use the trick with distributing points because it tends to give more organic results. Let's add distribute points in volume, and I will set the density to really big number, in my case 89999999488. Yes, big number. Now we are ready to set the point radius. I will set it to 2 mm. Finally, let's add points to volume and set the resolution to 400. Now we are ready to convert back to mesh. Let's add volume to mesh node. Our result is a little bit noisy now. Let's add the smooth group and set the iterations higher. The final step is to set shade smooth, which will just make our mesh look smoother. And that's it. We created our icing. We can play with the seed and settings to create different variations and choose one that you like. We can also create a new bake node to improve our future workflow. So, that's it for this part. I hope you like it. In the next part, we'll be working on improving our sprinkles. We'll make each of them completely different and we'll create custom attributes to allow for different colors inside the material. Thanks for watching. If you want to support my channel, you can check out my Blender add-ons and asset packs, link in the description. You can also download the donut file from this tutorial, links also in the description. In the last part we learned a bunch of new things and created this nice looking icing with droplets. Today we'll go back to our sprinkles because they are quite simple compared to our icing geometry. So, how can we improve it? That will be a topic of this video. Our goal in this tutorial will be the randomization of particles. Currently we have different rotations and scales which already make it look nice. But I want to take it one step further. To add extra details, we'll create a random radius to randomize it on our curves, and furthermore, I want to add slight bending to each sprinkle. And best of all, each sprinkle will have different bending. Finally, to create nice shading, I want to add a bevel on the edges of our sprinkles, and on the topic of shading, I will also create a new attribute for our material to randomize each sprinkle's color. So without further ado, let's jump into Blender and continue our work with geometry nodes. So, last time when we worked on sprinkles, I left the Realize Instances node. This will be really useful now because it will allow me to edit each sprinkle separately. First of all, let's add our bending. If you look at the reference image, you can see that sprinkles are often slightly bent. I want to recreate that in our system. To do that, we'll need slightly more geometry. And by slightly, I mean just one more vertex in the middle of each curve. To do that, we can use a resample curve node, just before our instance on points node. Here, just after the curve line, let's add the resample curve node. This time, we'll not be using length mode, instead I will use count mode. This is because I want to create exactly 3 points: endpoint, midpoint and start point. Let's set count to 3 then. Now, why do we need this midpoint anyway? Because what I want to do is move the midpoint randomly. Then, with a little bit of smoothing, we'll have this nice bent particle. So, let's add a set position node here. First, we need to create some sort of selection field to be able to select the midpoint. Because we are working with curves, there is a perfect node for that. Let's add an endpoint selection node. This node allows us to select points in curves starting from both endpoints. Let me show you this example. As you can see, we have a simple curve. If you start selecting more on the start size, we'll have more selection here. If we increase end size, we will have more selection at the other side. We can create any combination we like. So, to select a midpoint, in our case, we need to first select both endpoints, and to do that, let's set endpoint selection to 1 and 1. Now we can invert the selection with a simple not node. Great. If we play with the offset inside the set position node, now we can move midpoints around. Now we need to make it random. There is a node perfect for creating random values. Do you remember its name? It's the random value node. This time we can set its mode to vector because I want to move my midpoint in all three directions for the best randomization. We can play with the min and max range. Values are gonna be really small, as you can see. We can even add two multiply math nodes to have a better control over the setup. I will multiply my first value by a small number. For the second multiply, I will use the same number but negative. We can use a single value node here that will control our bending strength. Now we can clearly see what we are doing. We can also plug in our group seed. So, we have this little arrow shape now. We need to make it smoother to really create a bent line. For that, I want to use our smooth group, but there's a little problem. We don't have enough geometry to do that. Let's add a smooth group. As you can see, the smoothing just makes our particles smaller. Remember, we have only 3 points on each curve, so there is no way to make it nice and smooth. We need to resample our curve first. So, let's add a resample curve node and set the mode to length. I will set it to 1 mm. Great. As you can see, our smooth node works well, but it still makes the sprinkles shorter. We can reduce this effect by just making our curve line slightly longer here. Great. Let's preview our mesh now. As you can see, we have a nicely bent sprinkles and each one is completely unique. Now we are ready to add one more additional detail. Currently, our sprinkles have a constant radius along their length. However, sprinkles are often thinner or thicker in different places. We can do that really simply, just like we did with the icing droplets using the set curve radius node. Let's add this node here after smoothing. To control the radius, I want to use a noise texture. We've used noise a few times before, so nothing new here. Let's add the standard setup with a noise texture, offset coordinates group, and group input. If we plug the noise texture directly into the set curve radius node, we won't see much. This is because our noise is much too large right now. Let's preview it on top of our geometry. Remember, noises in Blender are usually created in 3D space, so we can preview the same noise on different geometries, even on different domains. let's change the scale of noise, and perfect. That's it. To control the strength and contrast, I will use map range node here. Let's play with it a little bit. Now you can see a difference. It's really subtle, but it creates additional details in our donut, and thanks to that we'll have more realistic results. Great. So, the last thing I want to do with our sprinkles geometry is to add a bevel. Unfortunately, there is no bevel node currently inside geometry node. But don't worry, we'll create a bevel effect for our particles differently, with just a few nodes. Here's the approach I choose. First, we'll extrude our circular faces and then scale them down a little bit. Repeat the process one more time and set the shade to smooth. Great. We have a nice looking bevel. So, let's do this. First, let's add an extrude mesh node at the end. Uncheck the individual option. Now we need to provide a selection. How can we select only circular faces? By using the endpoint attribute once again. We cannot use it directly here because this is a mesh, not a curve. But we can store it just before our conversion as a custom attribute. Let's do that. Let's add a store named attribute node and name it endpoints. Let's duplicate the endpoint selection node and plug it in. I will change the type to boolean. If you look at the spreadsheet now, you can see that we have our attribute here after conversion too. Great. Let's use it with a named attribute node. Remember, I added this node to my quick favorite, so I just need to press the Q key and select it. Let's search for a custom attribute. Now we can use it as our selection. Perfect. So let's set the offset value to something really small. To recreate the first bevel segment, I want to scale those faces now. We can do this simply with the Scale Elements node. Remember that node? We used it before. We use it at the beginning of the creation process of our donut. It allows us to scale each face at its own origin. We just need to plug in a selection, which will be the top output from the extrude mesh node. Let's adjust the scale a little bit. And there we have our first bevel segment. To create more realistic results, I will add a little bit more resolution with one more segment. Let's duplicate the extrude mesh and scale elements node and plug them after. Now, let's make the scaling a little bit smaller. And that's it. We've created nice beveled geometry. To make the results look better, we can set the shading to smooth. But this time, instead of using the Set Shade Smooth node, I want to add the Smooth by Angle group. This group comes with Blender by default and works like an auto smooth option. Let's select Ignore Sharpness and play with the angle value to create the desired results. Let's join our new sprinkles with the icing. Perfect. Our donut is starting to look really nice. The last thing in this tutorial will be a new material for the sprinkles. As you can see, donuts often have colorful sprinkles, but currently we have only a single color. Let's fix that. To do this, we will need a new attribute that we can use inside the shader editor. Let's add the store named attribute node at the end and name it random ID. I will leave it as a float. What I want to create is a random black and white value, so every sprinkle should have a different value between 0 and 1. To do that, we first need to be able to separate the sprinkles. How can we do that? One option is to use the mesh island index. Let's add the mesh island node. This node has two outputs. Island index, which outputs a different number for each separated element of the geometry. Perfect for our use case. The second output, the size output, which tells us how many mesh islands there are. In our case, it will tell us how many sprinkles we have. So, how can we use it? With our random value node. Let's add it and plug it into the store named attribute. Currently we have this noisy pattern because random value node outputs different value for each point of our sprinkles mesh. But there is an input we've ignored, the ID input. Let's plug the island index into it. Suddenly we have our desired effect. Each sprinkle has a different color. Why is that? You can think of the ID input as creating groups. We basically tell the random value node that each piece of geometry with a different ID should have a new random value. In this example, you can see how dividing into group works. Each sprinkle has a unique island index. That's why each sprinkle has a different random value. Perfect. Let's jump into the shading tab. Let's search for the attribute node. Now let's copy-paste the random ID name to make sure we don't make any spelling mistakes. As you can see, we can preview our attribute. The last thing we need to do is to add a color ramp node. Set it to constant to have just a few colors. And now let's pick a few colors. Let's plug it into the base color and that's it. We've created really unique particles for our donut. Great job. There's one little problem that we'll cover in the next part. If you zoom in on our particles, you can see that some of them are intersecting. We could increase the Poisson distance, but this would make our sprinkles look a little bit weird. And there would also be too few of them. Instead, we'll use a better method. We'll delete the intersecting sprinkles without changing the placement of the current particles. For that, I will introduce you to the repeat zone in Blender. So, stay tuned for the next part. You've come a long way with geometry nodes, so congratulations to you. Great job. In this part I want to introduce you to the one of the most exciting nodes in recent Blender releases, loops, or as it Blender called it, the repeat zone, or just repeat in the new Blender 3.3 release. Repeat is a unique combination of nodes that allows you to repeat some parts of your network to create unique results. I will show you how it works and how to use it, along with a few tips on this simple example. So, we have a simple default cube. I will now add a repeat node by searching for it. This is a repeat nodes duo. It consists of two nodes, an input and an output, and also a zone between them. Here. So, how does it work? Let's plug our default cube geometry into the first node, geometry input, to find out. One of the most important settings here is the iteration number. It tells the repeat zone how many times it has to repeat itself. If I change it to 12, everything that is between the input and output nodes of the zone is repeated 12 times. Let's add a simple set position node to better see what I'm talking about. Let's add a slight offset in the z-axis. And now, if we change the iteration number, as you can see, we are offsetting our cube more or less. What is happening is that in the first iteration we are offsetting the cube by 0.1 meter, and then this offsetted geometry is taken from the end of the zone to the beginning. In the second iteration we are offsetting the cube once again. This is extremely powerful addition to the geometry node system, and you can do a lot of interesting stuff with this. Besides changing geometry with simple nodes, we can also use fields to guide our repeat zone and even create physics simulation, but for that, however, the better choice will be the simulation zone, which is correlated to the scene timeline. Let me show you this example of how you can use fields inside the geometry node's repeat zone. So, I will delete the set position node and instead use the extrude mesh node. Let's add it. Wow, a lot is going on. Let's decrease the number of iterations to better see what we are doing. I will also add a scale elements node to scale the top faces of the new extrusions. To avoid extruding every single face, I will use a random value as a selection for the extrude mesh node. What I want to do now is to make each next extrusion a little bit longer. To do that, I will need to loop attributes. As you can see, we can drag and drop another wire from out the repeat zone. I will add a math node and connect it to the repeat zone. Let's change the mode to add. Now, with every iteration of this loop, the value is going to increase by this amount. We can preview it inside the spreadsheet editor. In the first iteration, we have a base value that we can set here. Then, we are adding to it our value here. This value then goes to the end node of the repeat zone, and in the next iteration, we are starting not with the value we set here, but with the value that goes to the end of the repeat zone. We are looping this value, this attribute, so the data flow looks like this. With each next iteration, this value gets bigger. Let's test it by plugging it in as our extrude offset scale value. As you can see, these smaller extrusions are getting longer. When we increase this value, or even better, change it to multiply, the extrusions will get even longer. So, this is the basic concept behind the repeat zone in Blender. So, what we are going to do with this repeat zone for our donut? We will use it to fix one error that we currently have inside our sprinkles system. The intersecting sprinkle particles. If you look closely at our sprinkles, you will notice that some of them are intersecting. We can try to increase the minimum distance at the beginning of the sprinkle setup, but then our sprinkles start looking too even, a little too low density and a bit boring. What I intend to do is to leave the particles as they are and then delete the particles that are intersecting. And for that, we'll use the repeat zone. So, without further ado, let's start. First of all, I will tag a new reroute node from our sprinkles. Now, I will add a new repeat zone. So, how should our system work? Let's break down our task into smaller steps to make things cleaner. First, what I want to do is iterate through all my sprinkles. I will select one and check if it's intersecting with any other sprinkle. If yes, I will delete it. If not, I will add it to a new sprinkles group. So, first of all, we need to iterate through all sprinkles. To do that, we need to know the current total number of sprinkles. We can get that information using the mesh island node. It will give us information about the individual mesh island count. But there's one small problem. We cannot connect a field to the iteration number of the zone. We need a single value for that. For this, we can use simple workaround with the help of attribute statistic node. Let's add it. Now, to make it work, we need to make two more connections. First, let's connect the island count output to the attribute input. As you may notice, all output of the attribute statistic node are single value ones. They are circular shaped. So, what we can do is take the max value and use it as our iteration number. Thanks to that, we ensure that we will iterate through each sprinkle. Now, we need to work on every sprinkle individually. For that, we need to divide the work in our repeat zone into three main steps. First, we separate a single sprinkle, different for each iteration. Then, we'll perform a check on it, and after that, if it is not intersecting with anything, we will join it to the new geometry. So, let's first learn how we can separate our sprinkles and join them back together. To separate geometry, we'll use the delete geometry node because we don't need the other separated geometry. We only need a single sprinkle. Now, we need to create a selection. For that, we can again use a mesh island node. If you look at it, you will notice it also has a second output, island index, which is a unique number assigned to each mesh island. So, in our case, it will essentially be a sprinkle ID. We can easily use it to separate a different sprinkle at each iteration. Let's add an equal node and plug into it our island index and iterations from the repeat zone. With these fields, we can select a single sprinkle. However, for the delete geometry, we need to select an inversion. So let's add a boolean not node and put it after the equal node. Now let's plug it into our delete node. Great. Now, from this output, we are getting a different sprinkle at each iteration. Now we just need to join them together with a simple join node. Let's add it and plug it into the output of the zone. Now, let's plug these two cables into it. So, we are back to where we started. Great. So, what is going on here, you may ask? What we are doing now is basically separating the first sprinkle and adding it to a new geometry. Then we separate the second sprinkle and join it too. And we are doing that for every single sprinkle, ending up with basically the same geometry at the end. So, the last thing that we need to do before joining our separated particle into the particle group is to check if it's colliding with our current new geometry of the particles. To do that, we will need to check if any point of this separated sprinkle is inside the newly generated sprinkles. For that, we will need to develop a custom group named isInsideVolume that will tell us if the geometry is inside of another geometry. This might sound complicated, but it will be just a few nodes, and after all, after the creation, you can just reuse this group in your next project without need to worry about how it works inside. So, how do we check if the point is inside another geometry? With a raycast node. It is a really effective solution, and I will show you how it works. First of all, we need a raycast node. What this node does is shoot a ray from the currently evaluated element, like a point, and then this ray can search for a hit with a specific target geometry. It can then give us information about that hit, like if it hit at all, the hit distance, position, normal, or even attributes. It's a really fast node, which makes it extremely useful because we will gonna perform this check each time for each sprinkle, so a lot. So let's shoot rays in random direction with a random value node set to vector. Now we need some target, and for that we will use the geometry output from the first repeat zone node. Thanks to that, we'll make sure that before adding a new sprinkle, we will check if it is not colliding with any existing ones. So let's connect it. Now we have our source, target, and the ray direction. What's next? To check if the point is inside the volume of another sprinkle, we will use normal information. For better understanding of this, I will show you this example. Let's imagine that we have 2 points. One is inside the cube and one is outside. We are shooting the rays in random directions. Let's assume that both of these rays hit the cube. Let's draw the normal vectors now. If you compare the angle between the ray and normals, you can notice that if the point is inside the volume, the angle will be larger than 90 degrees. And if the point is outside the volume, the angle will be smaller than 90 degrees. Knowing that, it is really easy to check if the point is inside or outside of the volume. Now, how do we check that between two vectors easily in Blender? With the dot product vector math node. What is the dot product? It is a math operation that basically tells us how the vectors are oriented to each other. If the value is equal 1, then they are facing the same direction. If the value is equal to 0, then they are perpendicular. And if the value is equal to -1, the vectors are in the opposite directions. Knowing that, we are ready to finish our Ice&Snow volume group. Let's add a dot product node and connect it to the hit normal and random value node. Let's plug it now as our output and name the socket. So, we now can check if any point is in or out. But we don't want to delete only a few points of the sprinkle. If any point of a sprinkle is colliding with the rest, we want to delete the whole sprinkle. So we need to add one more thing to our repeat zone setup. And that is the accumulate field node. Let's add it. This is a little bit more advanced node. It allows us to analyze fields and use them in a very specific way. What we will use is the total output of this node, which basically adds all fields within a group ID together. So for example, we have a cube and each point of that cube stores an attribute with a value of 1, the accumulate field for the point domain will be 8. So, why do we want to use it? Because now we can add all Ice&Snow volume values together for each sprinkle separately, and if the value is larger than 1, that means that some point is inside the volume. So, let's connect to accumulate fields the Ice&Snow volume group and as our group ID the island index. With the selection, the last thing that we can do before is change the accumulate field type from float to I was gonna say boolean, but there's no boolean actually. So it will work anyway, so we can leave it at float. So let's just add another delete node after the previous one, and as the selection we're gonna use the total output. Let's wait a second to calculation. And as you can see, some sprinkles disappeared now. If we zoom in, we can see that most of the sprinkles aren't intersecting anymore. The system is not perfect, but works pretty well. We can try to increase our original density a little bit now to make more not intersecting sprinkles. But remember, our setup is pretty heavy, so don't make too many of them or Blender may crash. So, this will be it for this lesson. I hope you learned something new and had fun with the repeat zone. These new repeat nodes are a really powerful addition to the geometry node system and can be really useful in many different scenarios. It's time to add final details to our procedural donut, as well as creating some final, better looking materials to create a nice final render. In terms of the geometry nodes improvement, I want to add two things. First, if you look at the sprinkles and how it interact with the icing, it just looks like there's no interaction, no change in the curvature of the icing. There's no tension. I would like to add some of this effect to the icing. The second improvement would be adding some particles to the dough to make it a little bit more realistic. It would be a nice recap of instancing. So, without further ado, let's jump into geometry nodes. Let's work first on the improvements for icing. As I said before, I want to add some tension. For that, we for sure need icing geometry and sprinkles. So, let's create some reroute node to keep our geometry nodes network clean. Great. So the idea for this system is rather simple. First, we need to create a selection attribute that will select the areas near sprinkles, and then, based on that selection, we'll offset icing geometry in the normal direction. The last part will be just some smoothing to make this effect more organic and natural. For the selection, I will use the geometry proximity node. It is an extremely useful node that allows us to check proximity/distance between different geometries, which is perfect for our use case. Let's plug it to our sprinkles. Because sprinkles are our target, we want to use a selection attribute on the icing geometry. Let's now preview the distance output with the Ctrl-Shift shortcut. As you can see, it's pretty dark noise texture. The darker the color, the closer this area of the icing is to the individual sprinkle. So now we need some sort of a threshold. For that, the less than node will be perfect. Let's drag and drop from the distance output and search for the less than node. Now let's adjust the threshold manually. I will type something around 0.001. I know, pretty specific. Perfect. That should be good. So, we have our selection field. Now it's time to create the offset in the normal direction. So as you remember, the normal direction is the vector that is perpendicular to the surface. That's why we want to use it. Because what I want to do is basically inflate our icing, but only in specific part. It's the same action like Alt-S shortcut in the edit mode. So, let's add a position node to our icing geometry. Now we need to specify the offset. For that, we will use the normal node for sure. And to control the strength of it, I will add a vector math scale node, which is basically one number multiplier for the vector. Because of how small this number needs to be, I will also add the classic math multiply node and set it to 0.01. I will set the other value to 0.05. Let's plug this now to our offset input in the set position node. Okay, the whole donut's icing is inflated now, but we plug the selection from the less than node. Great, it works as expected. So, we can now see that the offset is being applied only where there are sprinkles, which is exactly what we wanted. Great. The effect now is a little bit blocky. Let's add our smooth node group to make it look more organic. Adjust the number of iterations and great. This will be our final icing geometry. Let's preview the whole donut now. As you can see, this icing tension is a really nice addition to the overall look of the donut. It is a really small detail, but it was really fun to make individually with so few nodes. So, the last part that we will do with geometry nodes in this series is the addition of particles on the dough. So, this will be rather simple, nothing new here, just a quick recap. This is the final result. As you can see, we had to distribute many points on the dough geometry and then place small icospheres instances on them. To create more random results, I used noise texture to randomize the point distribution density, and after that I randomized instances itself by randomizing the scale differently in different directions, and then I also randomized the rotation. So pretty simple. If you want, you can try to recreate this last element by yourself. Pause the video and try to make those particles. I will show you my solution after a few seconds. So, first of all, we need our dough geometry. Then, we create the distribute points on faces node. To make distribution more uneven, I will use the noise texture. Let's change the scale to 30 and plug our offset coordinates group and main seed. Then, let's adjust the contrast of the noise with the color ramp node. I will use the viewer node to preview the colors on the donut geometry and adjust the color ramp a little bit. I will change the mode of the distribute points on faces node to Poisson disk and plug our color ramp as a factor. Now we need to adjust some settings to actually see some points. You can see the results before and after. The next step is to add an instance on point node, and as an instance I will use a simple icosphere with a really tiny radius. Now it's time for randomization. Let's add scale instances and rotate instances node. Plug them in. Now, for both the rotation and scale, I will use a random value, vector type, node. We can play with those values a little bit. And that's great. now we have pretty random results. We can plug those random values nodes to the main seed. The last thing is to set a new dough particles material. And same as for sprinkles, store the random ID attribute that we can use inside our material network. For the ID input of the random value node, I will plug the ID node, because these are still instances, so each one has a single value ID. Now it's time to finally join everything together. Perfect. That's it. You made it. This is our final geometry. We can use one last bake node at the end to make sure that we didn't need to wait for any calculations. So, now it's time to make a little order here and there. I'll put everything in the correct frames and name them and add some colors. The most important part is the inputs. Some elements like radius of the donut, seed, etc. are really important and would be nice to be able to control them outside the geometry nodes network. So, I want to create new group inputs and name them correctly. To keep some order, I also create panels that allows me to keep better order under my modifier panel. If you want to learn more about creating nice geometry based modifiers, check out my other video exactly about that. So, now it's time to work a little bit on materials. We have 4 of them: icing, sprinkles, dough and dough particles. Let's start with the icing material. Currently it's just a pink Principle BSDF. Let's add some noise texture. I will use Ctrl+T shortcut to add some UV mapping. Let's adjust the noise scale now. And now I will use a color ramp to better control the colors. This noise can now be used as our roughness. This will add nice extra tiny detail. To make it even better, we can duplicate the noise, change the scale and use it for the bump node input. Let's plug this to the normal input of the Principle BSDF, and that's one more nice detail. One more thing that we can do, and this will significantly improve the look of the icing, is subsurface scattering. Let's increase the weight of it under the subsurface panel. Great. We can adjust the main color a little bit now. Let's go to the next material, the sprinkles. We already had the color randomization, so the only thing that we would like to add is the noise texture for the roughness. We can just copy it from the icing material and adjust the noise scale a little bit. Also, adjust the color ramp. Now, let's work on the dough material. First, I will change the colors of the dough in the color ramp a little bit. Now, let's enable the subsurface scattering option too by changing the weight value. Much better. The next step will be to add some bumps. For that, we can again copy the nodes from the icing material. Let's plug them and adjust the noise scale and bump distance. Let's add another noise texture. I'll use the greater than node to select these big chunks of the dough and use this as the wake of the code to add nice sugar spots. To make this effect even better, I will add another Principle BSDF node and use it as my sugar material. Let's change the color to slightly more like dough. Now let's decrease the roughness and add same coating. I will also create a new noise texture for the bump effect. Now we can mix between this and this material with the use of the Mix Shader node. As the mask input, I will use the output from the greater than node from here. To have better control, I will add Math Multiply node and decrease it a lot. So, this is the final dough material. Now it's time for the dough particles. For them, I'll use the same color ramp as for the dough, to make sure the colors are similar. Then I will randomize the color a tiny bit with the random ID node and hue saturation value. It will be a really subtle change. Great. So, that's it. This is our final donut. Now let's just add a plain mesh as a ground, some wood texture, place the camera and press the render button. Thank you so much for watching. I hope you liked this series and learned something new about the Blender and the geometry node system. Geometry nodes are a really powerful element of Blender and I hope that you will use them in your future project. If you have any ideas for the future tutorials, write them in the comments. I will gladly look at them. If you want to support my channel, you can check out my Blender add-ons and assets pack, link in the description. I recently published geometry-based furniture assets that are using the new gizmo feature from the Blender 4.3 release. Thanks again for watching, see you again soon, and bye!